Hello there and welcome to the series Topics in Audio Processing and Music Technology. I am Renato, the instructor for these online materials, and the topic of today is DDSP Timbre Transfer Demo. This is demo application developed by the guys from Magenta team. So if you go to github.com/magenta/DDSP, and here you find something about the differentiable digital signal processing. So this is a library of differentiable versions of common DSP functions. So if you're not familiar with it, I give an overview about this DDSP library in another tutorial. You can just go to our playlist and there you find the DDSP overview tutorial. And today we will get a demo application and we'll make a tutorial out of this demo. We will take a look at the timbre transfer that converts audio between sound sources with pre-trained models. This is what we are going to do today. If you click here, then you go to this Google Colab notebook. And this notebook is a demo of timbre transfer using the DDSP, the differentiable digital signal processing. It uses pre-trained model. The model here is trained to generate audio conditioned on a time series of fundamental frequencies and loudness. So this notebook extracts these features from input audio. Either we can upload files or we can record using the microphone, and then it resynthesizes using this model. So what I'm going to do first is we're just going to use this demo application, go through without looking at the concepts and without looking at the code. We'll just run this application so we understand what's happening. And then we will start exploring and investigating the concepts behind it and also the code behind it. So let's get started. This notebook will have a user input. This audio signal will go through a neural network. Then there will be some digital signal processors, and then we'll have the final signal. It is also possible to train your model with your own sounds, and then they have a tutorial for it. That's very interesting. It's called the Train Autoencoder Colab, and then you can use your own model also here in this demo application. But today we're just going through this demo application and then we will investigate the concepts and the code behind it. They ask to make sure that you are using the GPU, so you can check here. We are using the GPU, and we will run pressing this play here. So let's get started. The first cell will install the DSP and define some helper functions and download the model. Now let's run this cell, and this is installing from a pip package. So this first cell is done. Now we have this cell here where we find Colab form, so we can choose here to record or to upload an MP3 or a WAV file, and here we can choose how many seconds to record. So have in mind that the audio that you record or that you will use an MP3 file or a WAV file, they should be monophonic, so it's a single instrument or voice. And then this cell will also extract the fundamental frequency F0 and loudness features. For this example, I am going to record just that I'm making some sounds with my hand, and then we will not upload. But later on we will see what's behind the scenes here, what they are using to record audio or to upload. So this is where we will start the tutorial itself. For now we are just running this application, and we are going to check what is happening. So let's run the cell. So here we have these sounds that I just made with my hands. So you can perceive a lot of wind and just some frequencies. So let's listen to it again. Then we have here this graph for the loudness. It is extracting some audio features, and it took 2.6 seconds to extract these audio features. And here we have is F0 in terms of MIDI note. And here we have the F0 confidence. And next, it asks for us to load a pre-trained model. So we have a violin, a flute, a second flute, a trumpet, and a tenor saxophone. And you can also upload your own if you have previously trained a model. So for this example, let's use the violin. So let's load the model. Just loading dataset statistics and restoring the model. Then we see also that we have now this pre-trained model, and we have some files. We're going to take a look at these files later. Then you can also modify the conditioning, so you can change the threshold for note detection. You can adjust some automatic adjustment. You can force pitch to the nearest note. You can also shift the pitch some octaves and adjust the overall loudness. So we're not going to change these values now. Let's just run with the default parameters. So here we have now this note on mask. So this is in blue the likelihood, and here we have the threshold, and then we have the note mask. So there is 1 here, here's 0, here's 1. We also have the loudness. So we have the original loudness, and then we have some adjusted loudness. And here we have our F0. So now let's re-synthesize the audio. So let's run the cell. So it's took 0.4 seconds. Here we have the original. So this is the sound that I made with my hand, and now the resynthesis, then it should sound like a violin. Oh, indeed, it sounds like a violin, and it's very similar to what I played with my hands. Here we have 2 plots. Here's the original, and here we have the resynthesis. So let's listen one more time. This was the original, and now the violin resynthesis. Oh, very nice, very interesting. Let's now change a bit here these parameters. So let's put the threshold so a quiet parts without notes detected. Let's make it a bit less. Let's auto tune. Let's put a bit more. The threshold. Let's make the threshold a bit smaller, just to see what we get from these new parameters. Let's run. Let's re-synthesize the audio. Oh, really interesting. Let's just change model. Let's go for a trumpet. So load this new model. Now it should be a trumpet. Let's leave this conditioning that we set before. Let's resynthesize the audio and let's listen to it. Well, this I already noticed doesn't sound like a trumpet to me. It has some, in the beginning, there's some resemblance of a trumpet in the beginning, but when we have these changes here it becomes very obvious that the model could not handle it very well, at least with these modifications also that we changed here. But now let's try one more model. Let's see how it sounds with the flute 2. Let's leave the threshold back in 1. So flute 2. Let's set these parameters here. Let's resynthesize this audio. It's also some kind of flute. It's definitely interesting, but I would not. I'm also not an expert in flutes, so I cannot really tell what's going on there. Last, what we are going to do, let's load a tenor saxophone. Let's resynthesize. It sounds like a saxophone to me, and it's also interesting because this is quite a hard audio that I just recorded with my hands, so there is a lot of windy noise, and the notes are not so quietly well defined when there is too much noise. And we see this structure vertical here in frequency. It sounds quite interesting to me. It's a saxophone, and this is not an easy original audio. There is some noise, there's a lot of this windy. We could be, if we use a record from an instrument, maybe we could achieve much better results, but it's interesting enough to investigate. So let's go back to the violin. This one is what I liked the most. But now I want to shift the F0 a bit. So let's shift 1 octave. Let's resynthesize. So this is the original. And the resynthesized violin. One octave higher. Let's go an octave lower. So that's it, what this demo application is doing. It's definitely very interesting. So we're uploading or recording our audio, and it extracts fundamental frequency and loudness features. Then we choose a model. We can change a bit some parameters of this model. Then we resynthesize. We also have these plots of the original and the resynthesis. So it's a time frequency spectrogram. So now that we know what this application is about, we tried with different parameters, with different models, we can start going into the details and to make a tutorial out of this demo. So the first thing we're going to do is we are going to select all cells, and let's expand the sections and also show the code. So As I mentioned before, this is a demo application developed by Magenta, copyright by Google. And there's this Apache license. And here we have one paper. So let's take a look at this paper. So this paper is about the DDSP, differentiable digital signal processing, and we will explain a bit about this the DDSP library, and they will show some examples. So I discussed a little bit this paper in our previous tutorial where I introduced this DDSP library. So here they explain different techniques and different DSP blocks that are part of this library. And here we have a general overview of an autoencoder that is used also in this example here. We'll have to come back to this where we see we have the original and target audio. We have an encoder. Here we have the F0 block that calculates the fundamental frequency. We have here a block for loudness. We have a decoder. Then we have a block for harmonic audio and a block for filtered noise. And we're adding these two. We're adding some reverb. Here we have our synthesized audio. And here is the multi-scale spectrogram loss. So this is a general architecture of an autoencoder that is used here in this DDSP, and you don't need to have all these blocks, and in fact you can have different types of encoders, different types of decoders. We have different DSP blocks that we can use, we have different losses, we have different effects, and we are going into a bit more detail when we start investigating here. So first is the install and import. They use here TensorFlow version 2. They install the DDSP library with pip, and they ignore some warnings about deprecation here. Then we are importing some OS, time, copy. Here we imported the DDSP, the DSP training, DSP Colab, utils. So we have autotune, detect nodes, play, record, spec plot. We are importing Gin. We're importing also from Google Colab files. We're importing librosa, matplotlib, pyplot, numpy, pico. Here we are defining the default sample rate. So it's taking care of importing packages and installing the DDSP. So one first thing we're going to take a look is Gin. So if we go back here to the Magenta DDSP GitHub, then down here they say something about Gin. Gin library is a superpower of dependency injection. They find it very useful for their experiment, but you need to be aware how to use it. So here is the Gin GitHub. So github.com/google/Gin config, and you find this link also here. And Gin provides a lightweight configuration framework for Python based on dependency injection. So these functions and classes can be decorated with a Gin configurable, allowing default parameter values to be supplied from a config file or passed via the command line using a simple but powerful syntax. So this removes the need to define and maintain configuration objects or write boilerplate parameter plumbing and factory code, expanding a project's flexibility and configurability. So they will use Gin. Next, there is this Google Forms to record or upload. It's defined here, and the number of seconds to record is defined here. So minimum of 1 second, maximum of 10 seconds, and in steps of 1. Then it will check if it's record or upload. Then if it's record, it's going to call this function record. The argument seconds is equal to the record seconds, which is defined here, and then there will be this audio variable. We will store the return what this record will return. If it's not record and it means it's upload, then it will call this upload function. Then we'll get file names and audios. Then it will print extracting audio features. So later on it will call this specplot audio and play audio. So specplot is here it plays the audio, and it will compute the features. So it will use the start time to calculate the time that it takes to extract the features. And here is their printing. Print audio features took 2.6 seconds in this case. So they have the time minus the start time. That gives you the time it takes to go execute this features computation. So they have here from the DSP training metrics compute audio features. It will be stored in audio features. Then the audio features loudness dB, here making as type of float 32, setting the audio features mod equals to none. We will check it out later. And they're defining some trim value -15. Then they are plotting the features, and this will be these plots here. So we have the loudness, F0 MIDI, F0 confidence. So audio features, it is calculated here, and there is a dictionary. We have a key loudness dB. We have also F0 hertz and also the F0 confidence, and here we see now that they are using the string -15. So they are taking from the beginning of this array until the end -15. So they are using a lot of functions now. We need to start looking at what are these functions doing. I will add one code cell here. The first what we see here is this function record. So let's investigate what record is doing. So here it is. This record audio from the browser in Colab using JavaScript. So if you are familiar with Google Colab, you know that this is a remote server and we don't have access to a microphone that is connected, could be connected to a remote server. There's no way we can use it, so we need to use the audio from our computer. So we use it through the browser. There is a tutorial on Guitars AI channel, and it's about the introduction to Google Colab for research, and there is a specific tutorial there with recording audio from the microphone. If you want to know more about recording audio from the microphone, you in Google Colab environment, you can take a look at this tutorial. But let's continue here. There is some arguments to this record function. Seconds is the number of seconds to record. By default is 3, but here we are using this, what we defined from the Google form. Then the sample rate is the default sample rate, and there is some normalized dB. So this normalizes the audio to this many decibels and returns an array of the recorded audio at that sample rate. So here we have the JavaScript to record audio. There is this record.js code, so this JavaScript code. Then it will have some printing, starting recording for that many seconds. Then it uses the display JavaScript to run this JavaScript code. Then we have an audio string, which is the output.evolve.js. And then we have this finished recording, and we will have this audio string it will use this base64 decode, so we would have our audio bytes, and then it will return this audio bytes to NP, that will convert this audio bytes to NumPy. And this function is here from the DDSP library colab utils.py. So we could have a full tutorial just on how to record audio using JavaScript. That is not the purpose of this tutorial. So you can use this function record to record audio, and you can use in other projects if you want. So if you want to investigate even more, what you can do is, here we are at the Magenta DDSP, and you can go here to GitHub to the DDSP colab utils, and then you see this library with these helper functions for running the DDSP in Colab notebooks. So for example, here they import base64, and they were using base64 there. It's decode the base64 encoded bytes like object or ASCII string S. So this is, for example, when we went back to this record, they also will use these audio bytes to NP. So we go back here to the Colab utils, and here there is the definition audio bytes to NP. So it converges audio file data in bytes into a NumPy array using PyDub. So it takes as an argument a byte stream of audio data, a sample rate, and a normalized dB. So to normalize the audio to this many decibels, you can set to none to skip, and it will return an array of the recorded audio at that sample rate. So we took a look now at the base64 and also audio bytes to NP. So at this point, we will have our audio if we recorded by ourselves. But if we didn't record by ourselves, we can also use this upload. So let's investigate this upload. Close this. So upload, this is a function also from Colab utils that loads a collection of audio files from disk into Colab. It can be a WAV file or an MP3 file. As an argument, it takes a sample rate, so we sample recorded audio to this sample rate, and we also have this normalized dB that normalizes the audio to these many decibels. It will return a tuple of lists with file names and NumPy arrays. So this is why we have here tuple file names and audios, and then we are selecting audios 0 to be our array, and it also uses this audio bytes to NP. So here it creates a audio empty list and append this file audio to this empty list for fname in fnames. Fnames is a list, audio files.keys, and audio files is used using this files.upload. So we go back here, we see also the upload. This is the same definition what we seen before. So probably this files is from Google Colab import files. Let's investigate also this part here. Files.upload. So files upload, render a widget to upload local to the browser files to the kernel. So we have some HTML code that's being displayed, and it's used to upload the files. So what does it mean? It means that if we use here upload and then we will run the cell, so now it's displaying here this HTML that we can choose files, and it will open a way so we can import our files. So it's calling this upload function from the Google Colab utils, and inside this Google Colab utils it also uses this files upload. This files upload is from Google Colab files.py. So if you're interested in understanding how you can use some also JavaScript and HTML to upload files, you can go deeper here in this code. I also use here the base64 code, and this is what they are using here to record or to upload the files. Let's continue with further investigation. So at this point we have our audio as a NumPy array. So either we recorded by ourselves or we uploaded. This time, just to demonstrate, I'm going to upload. It's the same audio I recorded the previous time, but I just saved into a file, and now I'm going to upload. So I'll choose here, this is my file hand sound. It's uploading. It's 100% done. Extracting audio features. Here we can play it back. So it saved the hand sound as hand sound 1 because I had previously already uploaded, but I didn't record for the tutorial. Now it's calculating the features using this DDSP training metrics compute audio features. We are going to take a look at this in the next tutorial. In this tutorial we are going to see how they are plotting this spectrogram and how they are playing back audio. So now here we have our spectrogram. So we have time on this x-axis and frequency on the y-axis. Here we have the plots of the features. This is not the topic of our tutorial today. This we will take a look in next tutorial. So this time the audio features took 37.1 seconds to be extracted, and we can listen to the uploaded audio file. So it's the same what we've been using so far. And now let's take a look at the spec plot. So I will include a code cell here. Let's see, spec plot. So this is from the DDSP training plotting.py. We have this spec plot. I have some arguments. It takes the audio, and we have V minimum and V max, rotate through. So this probably is to rotate, to change the X and Y axis. A size, so here the size is typically 512 plus 256. We need to plot the log magnitude spectrogram of audio. If patch, take the first element. So this is what it's doing here. If the length of audio shape is equals to 2, audio is equal to audio 0. And here it will have the log magnitude. And to compute this log magnitude, it's using spectral operations compute log mag. So this is what we need to look. So here we go to the github.com/magenta /DDSP. Let's go to DDSP. Let's go to training. Let's go here to plotting. And here is the plotting utilities for the DDSP library, useful in Colab and elsewhere. And here they are importing from DDSP, they importing spectral operations. And here the first one is the spec plot, what we've seen before. So let's go back there. Let's import the spectral operations. Now let's spectral compute log mag. And here we have the spectral ops compute log mag return the safe log of compute mag audio, and the arguments are audio, size, overlap, and pad end. So this is on the spectral ops, and inside the spectral ops it uses also this compute mag. So first it computes the magnitude and then it takes the safe log. So let's see compute mag. And the compute magnitude is using TF, so TensorFlow absolute value. Here is computing the short time Fourier transform, then is returning the TensorFlow Float32 version of this magnitude. So we need to take a look what is this STFT. So it's a short time Fourier transform, and we have the differentiable short time Fourier transform in TensorFlow computed in batch. So what it's doing is first is computing the short time Fourier transform, then is taking the magnitude, then is take the safe logarithm of this magnitude, and then we have the log mag. So the STFT, we remove the channel dimension if present. Here we have the TF signal short time Fourier transform, and we have the frame length, the frame step, the FFT length, the padding, and we can also take a look at the TensorFlow signal short time Fourier transform. And here it is part of the TensorFlow signal spectral operations and computes the short time Fourier transform of signals implemented with a GPU or TPU capability and supports gradients. So they did here a short time Fourier transform algorithm using TensorFlow operations, so it can be used with GPUs and it can supports gradients. So we see that it's everything interconnected. So the DDSP library is based on TensorFlow, and it will use TensorFlow operations to build these DSP blocks. So we've seen it uses the TensorFlow signal short time Fourier transform, then it will have this DDSP spectral operations. We can also take a look at the safe log. Oh, it's not made a mistake here. So avoiding the taking the log of a non-positive number, what makes it safe. So TF where x is smaller or equal to this epsilon, and the epsilon is defined as 1 to the power of 10 to the power minus 5, and it will calculate the logarithm of this safe So it will replace all the negative numbers by this epsilon. By default is 1e to the minus 5, and then it will take the logarithm. So we've seen the spec plot uses the log mag, that uses compute mag, that uses the short time Fourier transform, that uses the TensorFlow signal short time Fourier transform. So if you're not familiar with short time Fourier transform and you want to learn more about it, I encourage you that you go to Guitars AI YouTube channel and Guitars AI GitHub. There you'll find many different tutorials. Especially there is the advanced digital signal processing. It's offered by Professor Schuller at the UMNL University of Technology, and also the multi-rate signal processing, and there we explain more about this time frequency representations and about the short time Fourier transform, and also about the Fourier transform and the fast Fourier transform. So all these concepts that they are basic into the digital signal processing. There are some tutorials available, but have in mind that these tutorials, especially the ones from the UMNL University of Technology, they are targeted to master's degree students, so there should be already a knowledge of these basic signal processing techniques from the bachelor's degree, but still is possible to refresh or to catch on. But let's move forward. So we already know how to plot with the spec plot. Let's just take a look once more. Spec plot. After it gets the log magnitude spectrogram, it will rotate if it's the rotate is true, and be rotating 90, and then use pyplot match show. It will take this log mag and it will plot using this match show. And here we have just taking some ticks, having the X label and Y label, and we have this plot here, so they don't show any values in the axis, but yeah, it's not really useful if you don't know much about this plot. You don't know what the frequencies are or what the time is, but still just to visualize the audio that we uploaded or recorded. We can also take a look, if you're not familiar with NumPy rotate 90. Let's take a look what it's doing. So it rotates an array by 90 degrees in the plane specified by axis. Rotation direction is from the first towards the second axis. So it returns a rotated view of an array. It's an array of 2 or more dimensions. Now here's one example. We have this M, it's an array 1, 2, 3, 4 type integers. When you rotate this, you have 2, 4, and 1, 3. If you rotate in another axis, then we will have 4, 3, and 2, 1. So you can rotate many forms. You can define the number of times the array is rotated by 90 degrees, and also the axis. So the array is rotated in the plane defined by the axis, and the axis must be different. So this is what rotate is doing. Let's close all this help that we investigated here. Let's go back to the spec plot to see if we are missing something. Spec plot. So we've seen the compute log mag, we've seen the rotate. Let's take a look also in this match show. So let's go on pyplot. in case you are also not familiar with this function. So display an array as a matrix in a new figure window. The origin is set at the upper left and corner. Rows are displayed horizontally. The aspect ratio of the figure window is that of the array, unless this would make an excessively short or narrow figure. So from a function from pyplot, matplotlib, and it plots an array as a matrix. So I think we finished everything from the spec plot. We know how to plot, and now we have more information about this spectrogram. So before we just see maybe some frequencies, some time, but now we understand the default values. We need to look at the compute mag. Here we have some sizes, and also we understand that it's the log magnitude spectrogram. Now let's move to playing back this audio. So much probably they are wrapping around some HTML5 audio controls, and this is done by the play audio. So let's investigate what this play audio is doing. So play, it is a function from DDSP Colab utils. It creates an HTML5 audio widget to play a sound in Colab. And this function should only be called from a Colab notebook, so it will not work if you're not in a Colab notebook. As an argument, it takes an array of floats, as a 1D or 2D array-like container of float sound samples. The values outside the range of -1 and 1 will be clipped. It also needs a sample rate, so the sample rate in samples per second. There is this argument called ephemeral, that if set to true, the widget will be ephemeral and disappear on reload, and it won't be counted against real-time document size. And there is also play, that if it's true, it will automatically start playing the sound. Once again, if patched, it takes the first element. We've seen here this before. It is going to use this kind of normalizer they're calling here. So there will be this array of ints, and they are using this mem file, it's IO bytes IO, and they wave write this mem file. There's the sample rate and the array of ints. Here we have this audio HTML for audio control, the source control, so it's wave base64, the base64 wave file. If your browser does not support the audio element, it will display this message here. Then we have here once again the base64 encode, so now it will encode to the base64. First it will decode from ASCII, the mem file get value, and it will close this mem file, and then for this part if it's ephemeral or if it's not ephemeral. There are also other ways to play this file. We could use IPython display audio, but they decided to go for this way here. So there are some things here. Let's see, for example, what this numpy info is doing. So machine limits for integer types. I'm setting some machine limits for integer types. We also have here is IO bytes IO. So we need to import IO first. So it's a buffered IO implementation using an in-memory bytes buffer. Then we have this wave file write, and it will write a wave file. So this wave file here is from SciPy IO wave file. And now we can take a look at the wave file write. And we have here, write a NumPy array as a wave file. As a parameter, it takes a file name, this is a string or an open file handle, output a wave file. There is the sample rate and also the data array. And also it writes a simple uncompressed wave file. To write multiple channels, you need to use a 2D array of shape and number of samples and number of channels. The bits per sample and PCM float will be determined by the data type. Here we have some common data types. We have the 32-bit floating point, goes from -1 1 is a NumPy float 32. Then we have 32-bit PCM and 16-bit PCM or 8-bit PCM, and then we have the NumPy types int32, int16 or uint8, and these are the minimum and the maximum values. And here we can already see that the 8-bit PCM is unsigned. And here is an example to create a 100 Hz sine wave sampled at 44.1 kHz and write it to a 16-bit PCM mono. Okay, so we've seen here how to plot the spectrogram and also to play the audio. If you want to play also not in Google Colab, but if you're using in your local Jupyter notebook or you're using other environments, you can use different playing methods. So let's just comment this out. So here now I'm importing IPython display as IPD. Here I'm commenting out display. So when we execute this, there will not be any playing capabilities here anymore. We can insert a new code cell and then we display IPD audio. This is the audio which is the same that we got from here, the NumPy array. We need to determine the sampling rate. By default it's using the 16 kHz. So when we run the cell, we have and this is now not limited to Google Colab, and we can also investigate what this is doing. Also probably it is a wrapper around this HTML5 audio control. So create an audio object. When this object is returned by an input cell or passed to the display function, it will result in audio controls being displayed in the front end, and it only works in notebooks. So you need a Jupyter notebook to use this. And you can pass the data, could be a NumPy array, a list, a Unicode string or bytes. So NumPy 1D array containing the desired waveform, 2D arrays containing waveforms for each channel, string containing a file name, byte string containing raw PCM data, or a URL pointing to a file on the web. So here for another example, generating a sound, then you are playing it back. You also can play it back from a URL. You can play it back from bytes. So it's a class, and then we have different methods. There's also an autoplay. Here we have this audio controls for the HTML, and this is taking care of all the different types of data that it supports and the multiple ways of how you can play back audio. So here we see that you can use display from the DDSP library. It's imported here from the DSP Colab utils, and we have here the play. But you can also use the IPD, so the IPython display from the IPython library display.py. That's it for this tutorial, and In the next tutorial, we are going to now look into how to compute the features. So we have here the audio features. So there should be the loudness, and there should be the fundamental frequency. So we are going to take a look how we are generating these audio features. See you next time. We reach now the point where we will compute the features. So we will compute the F0, the fundamental frequency, and the loudness. And we come up here with this setup the session, and it's the DDSP spectral operations reset CREPE. Well, let's take a look about this function. And this is a function to reset the global state of the CREPE to force model rebuilding. So at this point, we are here at the spectral operations. And if we go to the GitHub on the spectral operations, we see here import CREPE. So what is CREPE? We are here at github.com/marl/CREPE, and CREPE is a monophonic pitch tracker based on a deep convolutional neural network operating directly on the time domain waveform input. So it was from 2018. At that time it was the state of the art. We are now in May of 2021, so I didn't follow up what is the state of the art now. I'm sure things have improved. There are a lot of great research groups studying this pitch tracking problem, but this one is good enough for our purposes, and it's the one that is used by the DDSP library. So here we have further details of the convolutional representation for pitch estimation, CREPE, and it's from the ICASP, so the International Conference on Acoustics, Speech and Signal Processing from 2018, and this is a paper from the University of New York. So here we are at the this paper, convolutional representation for pitch estimation. So they say that the task of estimating the fundamental frequency of a monophonic sound recording, also known as pitch tracking, is a fundamental to audio processing with multiple applications in speech processing and in music information retrieval. And they tell about some techniques such as the PYN algorithm that's based on combination of DSP pipeline and heuristics, and they perform well on average, but there are cases which they fail to correctly estimate the pitch. So in this paper they propose a data-driven pitch tracking algorithm, the CREPE, that's based on neural networks, and they show that the proposed model were state-of-the-art by the time they published this paper. And here, PDF, we have here the paper where they will explain this model. So we have here the architecture. So it's a deep neural network that operating directly on the time domain audio. And here is the architecture. So we have 1024 raw audio samples, and we have a convolutional layer, size is 512, stride is 4, and they have max pooling 2 and 1024 filters. And here they will have another convolutional layer, size is 64, and they have 128 filters. So then they will go from 64 by 128, and there is another convolution, no layers. Yes, also have some max pooling. They have a series of convolutional layers, so they go from 128, 64, 32, 16, 8. Here we're keeping 120 filters. Now they decided to go to 256 filters. Then they reshape, they go to 2048. They have this F fully connected layer, and it goes to 360 nodes in the output layer that corresponds to a specific pitch value defined in cents. There are 6 convolutional layers that result in 2048 dimensional latent representation, which is then connected densely to the output layer with a sigmoid activations corresponding to a 360 dimensional output vector y hat. And they explain that a cent is an unit representing musical intervals relative to the reference pitch, and is defined by this function here, where they use the f reference to 10 Hertz throughout the experiment. And then this unit provides a logarithm pitch scale where 100 cents is equal to 1 semitone. Then they also use the resulting pitch estimate as a weighted average of the associated pitches according to this function here. However, they explain here that for the library they changed the weighted average, so this is slightly different from the paper, and this here only focuses on the neighborhood around the maximum activation, and they found that it's shown to improve the pitch accuracy. The target outputs that used to train the model are 360 dimensional vectors where each dimension represents a frequency bin covering 20 cents, and the same as the model's output. And the bin corresponding to the ground truth fundamental frequency is given a magnitude of 1. So they explain here they use the ADAM optimizer with a learning rate of 0.002. They have here the binary cross entropy between target vector y and the predictor vector y hat. And the binary cross entropy is given by this equation 4. Then the best performing model is selected after training until the validation accuracy no longer improves for 32 epochs, where one epoch consists of 500 batches of 32 examples randomly selected from the training set. Each convolutional layer is preceded with batch normalization and followed by a dropout layer with the dropout probability of 0.25. And they implemented using Keras with a TensorFlow backend. So they also explain the data set. They used the data set. Let's see. They used 2 data sets. The first is RWC Synth, contains 6.16 hours of audio synthesized from the RWC music database, and is used to evaluate the PYN algorithm. So you can check here the reference for this RWC music database. Then they explain the methodology. So they trained the model using a 5-fold cross-validation, and they used 60-20-20 for train validation and test split. They evaluate the algorithm's pitch estimation, measuring raw pitch accuracy and raw chroma accuracy with 50 cents thresholds. Then they compare their CREPE against the state-of-the-art at the time, monophonic pitch tracking. It was the PYN and the swipe. You also have reference if you want to understand what they're talking about here. Then they show the results. They compare their method with other methods, and here they have some conclusions. So they say that the robustness of the model could be improved by applying pitch shifts as data augmentation, so to cover a wider pitch range for every instrument. In addition to the data augmentation, various source of audio timbre can be obtained from software instruments. There's the nth dataset is an example where a training dataset is generated from the sound of software instruments. And here we have the reference, and you can go further if you are interested in understanding. So it's a very interesting convolutional neural networks model that goes from the raw audio and gives you pitch estimation, pitch tracking. And this is what they are using. So they're importing this CRE-PE, and it was developed by the Music and Audio Research Laboratory and the Center for Urban Science and Progress at New York University. So there are many interesting research going on at the New York University. They have this very interesting music and audio research group, so you should check out what you're doing. So here they use CRE-PE. Let's go back here, and they need to reset the global state of the CRE-PE to force model rebuilding. This is what they are doing here. Next, they are computing the features. They are just having this start time, and they use this time to compute the amount of time it takes to extract the features. And they have here this variable audio features, which will receive the return of this DDSP training matrix compute audio features, and this take the audio as an argument. And this is what we need to investigate now. So it is from the DDSP training matrix.py, and it's a function to compute features from audio. It takes here the audio that we recorded or we uploaded here. It also has some other arguments, and they are set to defaults. So there's the number of FFT, it is 2048. The sample rate is this 16 kilohertz. And if you look here, also in the CRE-PE, they have somewhere they say that they use a default sampling frequency. So the model is trained on 16 kilohertz. So if the input audio has a different sample rate, it needs to be resampled to 16 kilohertz. So audio features, there will be audio, and it will squeeze the dimensional. So it's a dictionary. Now we will have the audio features loudness, and then it will call another function from the spectral operations compute loudness, and it will take also some arguments like the audio, sample rate, frame rate, and the number of FFT. Then they have audio features F0 Hertz and audio features F0 confidence, and they have this other function from the spectral operations compute F0. Well, we need to investigate further. So as we were talking about the CRE-PE, let's first investigate the function that computes the fundamental frequency, and then we will see about loudness. So let's go back here and investigate compute F0. So it's on spectral operations from the DSP, and this function is non-differentiable and takes input as a NumPy array. So we see here that it's non-differentiable, doesn't support gradients if you use this compute F0, and it's being used here to extract features. So it takes a NumPy array of single audio example, and the shape should be the audio length. Then it takes a sample rate in hertz, a frame rate, so a rate of f0 frames in hertz, and they use Viterbi decoding to estimate f0. So the Viterbi algorithm is a dynamic programming algorithm for obtaining the maximum a posteriori probability estimate of the most likely sequence of hidden states. So this algorithm has found application in decoding the convolutional codes using in a CDMA and GSM digital cellular, dial-up models, modems, satellites, and is also commonly used in speech recognition, speech synthesis, diarization, keyword spotting, computational linguistics, and so on. And for example, in speech-to-text, the acoustic signal is treated as the observed sequence of events, and a string of text is considered to be a hidden cause of the acoustic signal. And here you can understand more about this algorithm. And this algorithm is used in a Viterbi decoder that uses the Viterbi algorithm for decoding a bit stream that has been encoded using a convolutional code. And you can also read about the Viterbi decoder here. And they can use, if it's set to true, it can use Viterbi decoding to estimate the f0. And then this function will return the fundamental frequency in hertz, the shape is n frames, and also the confidence in the hertz estimate, and it goes from 0 to 1. So they have a lot of steps here. They compute the f0 with CREPE, and they have the CREPE predict, and they pass all these arguments, and then they will have the f0 and the confidence, and then they do some post-processing on f0, so they will here pad or trim to the expected length. They changed, of course, the type to be a float 32. Also some post-processing of the f0 confidence, and they also pad or trim to the expected length. So this way now we will have the f0, and later on they will plot the f0 here, and also the confidence going from 0 to 1. Here we have high confidence of the estimate, this part here. These parts we see it's also high confidence, but then we have some low confidence areas also from here. So this is how they compute the f0 here, part of the audio feature. But there is also this loudness, and that's what we're going to take a look right now. Let's close this. Let's go back to compute audio features here. We've seen this part here, compute f0. Now we will see compute loudness and see how they compute loudness. So the perceptual loudness in dB relative to white noise amplitude equals to 1. It will take several arguments. It will take the audio as a NumPy array or tensor, and the shape should be the batch size and the audio length or the batch size. There is the sample rate, the audio sample rate in hertz, the frame rate, so the rate of loudness frames in hertz, the FFT window size, range dB sets the dynamic range of loudness in decibels. The minimum loudness corresponds to minus range dB per frequency pin. Reference dB sets the reference maximum perceptual loudness as given by this formula here. and the default value corresponds to white noise with amplitude equals to 1 and 2048 FFT points. There is a slight dependency of the FFT size due to the different granularity and perceptual weighting. And you can use TF, and then you can make this function differentiable by using TensorFlow. So by the default is not differentiable, so TF is set to false, but you can set it to true, and then most probably they will have here a part where they will use maybe NumPy, and another part that if it's set to true, it will use TensorFlow. So you can pick TensorFlow or NumPy. So if use the TF, if use TF, else NP. This is this lib here, which are defined to choose between TensorFlow or NumPy. Here they make input tensors for TensorFlow, so they take the audio and they make it TF float32 if TF, or use audio if TF is false. So for NumPy they will use the audio. Then they temporarily have a batch dimension for single examples. They're doing this here. Always there is this if is 1D, else audio, or if use TF, else STFT NumPy. So here they are using the short time Fourier transform, so they use the TensorFlow version if you want to make it differentiable, or use the NumPy version of the short time Fourier transform. So they're doing this, they're taking the short time Fourier transform, they are computing the power. Here they are calculated perceptual weighting, and they are using now LibRosa. Here they get the frequencies, and here they have the A weighting, also a very convenient function in LibRosa. So if you're not familiar with LibRosa, I highly recommend that you take a look. It's a very powerful library, very used in music information retrieval, audio processing. They have a lot of pre-built tools. And here the loudness will be the power dB, it's calculated from here, plus the A weighting. We've been talking about loudness, A weighting, power, but perhaps you're not familiar with these concepts. And here it is, some explanation from the book Fundamentals of Music Processing by Professor Meiner Müller from the International Audio Laboratories in Erlangen. This is part of the Fraunhofer Institute, and here they will explain something about the decibel scale, about loudness, and also with some examples. So from a physical point of view, sound power expresses how much energy per unit time is emitted by a sound source passing in all directions through air. And we calculated previously, I just showed that they are calculating the power when they're computing the loudness for the audio features in the DSP example we were talking about. Then the term sound intensity is then used to denote the sound power per unit area. And in practice, sound power and sound intensity can show extremely small values that are still relevant for human listeners. And then it exists something called the threshold of hearing, which is the minimum sound intensity of a pure tone that a human can hear. So going further here, they calculate some power here for this Beethoven excerpt from Beethoven's Fifth Symphony, conducted by the maestro Karajan. And here there is an example how to compute power. And then it comes to loudness. So dynamics and sound intensity correlate with a perceptual property called loudness, by which sounds can be ordered on a scale extending from quiet to loud. And loudness is a subjective measure which not depends on the individual listener. Age is one factor that affects the human's ear's response to a sound, but also on other sound characteristics such as duration and frequency. And here we have some curves. We have the threshold of hearing, we have the threshold of pain, and these contour lines, they can be approximately described by weighting functions. And we've just seen something that we're using LibRosa, weighting functions. So, based on psychoacoustic experiments, this perceived loudness of pure tones, depending on the frequency, has been determined and expressed by the unit phon. And this following figure here shows equal loudness contours, where each contour line specifies for a fixed loudness given in phons the sound intensities over logarithmically spaced frequency axes. And then these contour lines can be approximated by weighting functions. And here, for example, we have these weightings, and this defined by this standard IEC electroacoustic sound level meters specifications, and we have A weightings B, C, D, and here we have, for example, an equation for the A weighting. And here in LibRosa we have here, there is this LibRosa A weighting which is used by the DSP to calculate the loudness, and we have some examples how to get the A weighting for some CQ2 constant Q transform frequencies, for example. There is also a perceptual weighting and different weighting functions. We can take a look at the source code, and the A weighting compute the A weighting of a set of frequencies. Takes as arguments of frequencies and the minimum dB, and clip weights below this threshold, and it will return a weighting. And here is the example. So we see there is this weights 2 plus 20 times log. So there is a function here. Should be something similar to what is explained here. So this is an example here. For example, they will get chirp signal with equal power, and then the chirp signal with equal loudness, and we can perceive some difference. So this is with equal power. And here with equal loudness. So if you want to go deeper in these basic concepts, I highly recommend the Fundamentals of Music Processing by Professor Müller. It's a very good book with a lot of examples. And then we can go back now to where we were in computing, extracting this loudness feature to use in our DDSP example. They set some dynamic range, the average over frequency beams, they remove the temporary batch dimension, and they compute the extended length of loudness vector. Then they pad with minus range dB noise floor, or they trim the vector, and it will return the loudness. So at this point now we will have our features, and there's a dictionary. Audio features, it's a dictionary. So the dictionary has some keys: audio, loudness, F0 Hertz, and F0 confidence. And then you can access the data as you want. And then they are plotting. So they have here with pyplot, they are plotting the loudness, f0 and f0 confidence. And here we have our features. So at this point, we generated and computed some audio features that will be used in the next steps. At this point now, we are ready to load a pre-trained model. So here we have a Google Colabs form where we can choose a model. So there are some pre-trained model available, or you can upload your own checkpoint folder as a zip file. You can get your own model if you follow another tutorial by the guys from the Magenta team, where they teach you how you can train your own model, and then you can use in this application. Let's see here what they are doing inside this. So here they have the Google form, the defining a find model directory, and this function will iterate through directories until model directory is found. Then here they are checking if you selected a pre-trained model or if you want to upload your own. If you select one of the pre-trained model, this pre-trained model is stored in somewhere in the cloud. They will create a directory. So at the moment we just have the sample data in the hand sound that I have here. So they will create this content pre-trained if you choose one of the pre-trained models, or content uploaded if you upload your own files. Then here is the location of the pre-trained models, and here they're using this GSUtil. So GSUtil is a Python application that lets you access cloud storage from the command line. So here are the instructions of how you can use it. They are using here, and they will have here also a gin file. It's all part of this structure, this file structures that they define here. So that the DSP model snippet transfer, there is a date, then there will be the solo, the model that you choose here, checkpoint, the gin file will be operative config 0 gin. If you upload your own, it will be a zip file, so they will unzip here. They'll also get this gin file from the files that are inside this unzipped directory. Then they will load this data set statistics. We're going to take a look about this data set statistics later on. And what is interesting here is that they use this TensorFlow IO gfile exists gfile. And this function here, tfio gfile exists, determines whether a path exists or not. And there is some instruction on how you can use it. And they also using this gfile. So let's take a look what this is doing. So it's a file IO wrapper without thread locking. So the main roles of the tfio gfile mods are to provide an API that is close to Python's file IO objects, and to provide an implementation based on TensorFlow C++ file system. And there are also instructions here how you can use it. With this, they are loading this dataset statistics. Next, so now they have a gin file here, either if you uploaded or if you chose one model, and they need to parse the gin config. So for that, they are using this gin unlock config. Let's take a look at that. So it's a context manager that temporarily unlocks the config. Once the config has been locked by gin finalize, it can only be modified using this context manager. So they are unlocking config, and then they are parsing a config file. And we also will take a look in this function. In this parse gene config file, it takes as an argument a configuration file, the path to a gene config file. There is this skip unknown. This is a boolean indicating whether unknown configurables and imports should be skipped instead of causing errors. And it returns an instance of the parsed config file, includes and imports containing the final name of the parse files, a list of names of imported modules, and a list of the parsed config file includes and imports created from including nested gene files. So this is how they are parsing the information contained in the gene files. Then they will assume that there is only one checkpoint in the folder, and here will be this checkpoint. Next, they will ensure the dimensions and sampling rates are equal, and they will use this gene query parameter. So the gene query parameter returns the currently bound value to a specific binding key. So the binding key argument should look like something like this. You note that this will not include the default parameters, and it will return the value bound to the configurable parameter combination given in the bind key. So with this, they are getting a time step string. So they are querying the parameter F0 loudness preprocessor time steps. And sample string, they are querying the parameter harmonic end samples. And the hop size, they are dividing the end sample string by the time step string. And they have the hop size. Then they are having here the time steps, which is audio.shape of this NumPy array divided by the hop size calculated here, and the end samples is the time steps times the hop size. And here you can print the time steps for the trained model and the time steps for the resynthesis. Well, let's uncomment this. So very interesting to see everything. And remember that this audio here is a NumPy array, and is what we loaded in a previous. We have here the audio that we uploaded. So we are at this point here. Then they will have a list of gene parameters. Once again, they will unlock the config and they will parse the config of this gene parameters. Here they will trim all the input vectors to the correct length. So they have for a key in this list, the audio features key, so one of these. Then we'll have audio features key, and it will trim to the time steps for these keys here. And for audio, it will trim to the number of samples. Next, it will set up the model just to predict audio given the new condition. And here it will build model by running a batch through it. So the model is this DDSP training models autoencoder. We are going to take a look at it in the next tutorial. Here it will restore the weights and the parameters for the model that was saved in this checkpoint. We also got this checkpoint earlier here. And then it will build the model by running a batch through it. You compute the time. So the model, it will have as an input the audio features, training set to false, and then it will tell us how long it took to restore the model. Notice that now, just for the sake of not using the GPU free time, I'm setting to no GPU, so it may take longer to build a model by running a batch through it. But let's run this. So we see here, we don't have any new files. Let's run the cell. Let's choose the violin. So let's see the form. It's the violin. Let's run the cell. loading dataset statistics from content pre-trained dataset statistics. When we refresh here, we see that it created this pre-trained. Inside this pre-trained, we have this file here. We have the checkpoint.index, we have the dataset statistics.pickle, and we have the operative config gin. And it took 3.2 seconds. So now we have our pre-trained model loaded, and on the next tutorial we'll move on to investigate how does this model look like, what is the contents of this operative config gin, what is the content of this dataset statistics. And that's it for this tutorial, and I see you next time. We loaded the pre-trained model, and now we will start to understand this pre-trained model. So here we have set up the model just to predict audio given a new condition. We have our model is equals to the DDSP training models autoencoder. So let's take a look at this autoencoder model. And this is a class that wrapped the model functions for dependency injection with gin. And here we notice that we have a preprocessor, an encoder, a decoder, a processor group, and loss objects. Then we have the method to encode, that get conditioning by preprocessing and then encoding, decode, get generated audio by decoding and then process, get audio from outputs, extract audio output tensor from outputs dictionary of the method call, and here we have call, run the core of the network, get predictions and loss. Then we have here, it runs through the processor group, parse the outputs. If training, it will update the losses dictionary and will return the outputs. And we see that this class autoencoder is inheriting from the class model. So let's look the class model. And the class model wrap the model function for dependency injection with gin, and it inherits from a Keras model. And we see here that there is this method call that reset the losses dictionary on each call, and we have here also the method update losses dictionary. That's a helper function to run loss objects on arguments and add to model losses. There's a restore that restore model and optimizer from a checkpoint, and we are using here model restore checkpoint, so it will also calculate the time it takes to restore the model, and it will load this checkpoint. Then there is the get audio from outputs that extract audio output tensor from the outputs dictionary of call. And here we have the call. In this call we will run the forward pass and losses and create a dictionary of outputs. So this function must run the forward pass, add losses to self losses dictionary, and return a dictionary of all the relevant output tensors. Let's go back here to the autoencoder, and we see that we have preprocessor, encoder, decoder, processor, and losses. For that, we go back to the paper, ICLR paper. We discussed about this in previous tutorials. And here we have the autoencoder architecture. And we see that the red components are part of the neural network architecture. The green components are the latent representation. And the yellow components are deterministic synthesizers and effects. So not all these components are used all the time. And also we have different types of encoders, different types of decoders, different types of deterministic synthesizers and effects. We go back here to the autoencoder, and now we look at the gin configuration file. And here we have some parameters for autoencoder. So the encoder is set to none, so we will not have any encoder. The decoder is set to the RNN-FC decoder. The loss is set to spectral loss. Preprocessor is set to calculate the F0 in loudness, so it's the F0 in loudness preprocessor. So we have here the F0 latent representation and the loudness latent representation. And we have a processor group. So the processor group, when we go back, we go down here, we see that this processor group is formed by a harmonic, a filtered noise, add, and reverb. And we see here the harmonic, the filtered noise, the add, and the reverb. Then we'll have our synthesized audio. Then for every part we have some parameters. So we have the parameters for the processor add, is just the name, add. We have parameters for the F0 loudness preprocessor, then there are sometimes steps, parameters for the filtered noise, parameters for the harmonic, parameters for an oscillator bank, parameters for the reverb, for the recurrent neural networks fully connected decoder, parameters for the solo violin, and parameters for the spectral loss, as well as parameters for training, like the batch size, number of steps, and here also parameters for the training, such as the learning rate. So all the parameters that we need are set here in this gene configuration file. To investigate even further, let's go to the GitHub magenta/DDSP, and we go to DDSP training. So Magenta, DDSP, we're here in the differentiable digital signal processing. Let's go to DDSP, and here we have some files, for example, processor losses, effects, spectral loss. Let's go here to training, and let's take a look at encoders. So there is a library of encoder objects. Just have in mind that for this specific example, for this pre-trained model, there is no encoder, but I'll just list some available encoder. So there's a class C encoder. This is a base class to implement an encoder that creates a latent Z vector. We have MFCCs as latent variables distribute across time steps. We have ResNet sinusoidal encoder. So this encoder maps directly from audio to synthesizer parameters. We have sinusoidal to harmonic encoder that predicts harmonic controls from sinusoidal controls. We have one-hot encoder that get an embedding from the instrument one-hot. We have aggregate features encoder that take mean of features embedded in time. MFCC encoder that uses MFCC as latent variables. MFCC RNN encoder that uses MFCCs as latent variables compressed to single time step. MIDI encoder that encodes F0 and loudness to MIDI representation. Harmonic to MIDI encoder that encodes the harmonic synthesizer parameters to MIDI representation. Expression encoder that get latent variable from MFCC's loudness and pitch. And those are the encoders. For the decoders, we can take a look here at the decoders. So there's a library of decoder layers. Here we have the RNN-FC decoder, and this is the one used to call the decoder's RNN-FC decoder. So it's used by this model we are talking. It's a recursive neural network and fully connected stacks for F0 and loudness. So there are some predefined parameters here, but we also have here other parameters for the RNN-FC decoder. So channels 512, have layers per stack, RNN channels, RNN type, and here are some defaults, so we can also change using this configuration file. Then there will be some layers, input stacks, RNN in the output stack. Here is a method to compute the output, run RNN over the latents, and here's some final processing, and returns the out stack. The default type of the RNN is a GRU. So if you're not familiar with RNNs, or recurrent neural networks, is a class of artificial neural networks where connections between nodes from a direct graph along a temporal sequence. This allows to exhibit temporal dynamic behavior. They are derived from feed-forward neural networks, and RNNs can use their internal state memory to process variable length sequences of inputs. So here just a general overview of RNNs, and the type of RNN that we're using is the gated recurrent units, GRUs, and they are gating mechanism in recurrent neural networks. So the GRUs is like a LSTM, long short-term memory, with a forget gate, but has fewer parameters than LSTM, and that lacks an output gate. The GRU's performance on certain texts of polyphonic music model, speech signal modeling, natural language process was found to be similar to that of LSTM. So here you can take a look of gated recurrent units. So to go deeper into RNNs or gated recurrent unit, we would need a full series of the tutorials. That is not the purpose of this one, but this is here the decoder that they are using, that is here in this gene file, is the RNN FC decoder. We also will have here the harmonic, and the harmonic is part of the processor group. So we have synthesizers, harmonic. We can go here to the DSP synths, so a library of synthesizer functions. And we have tensor to audio. We have the harmonic, so synthesize audio with a bank of harmonic sinusoidal oscillators. And also here they will explain harmonic oscillator and additive synthesizer. So also we have a series of parameters. So as an argument, it takes fixed length of audio, of output audio. There is a sample rate, a scale function for amplitude and harmonic distribution inputs, normalize below Nyquist, so remove harmonics above the Nyquist frequency and normalize the remaining harmonic distribution to sum to 1, amp resample method, mode with which to resample amplitude envelopes, and here we have the filtered noise. So the filtered noise is also part of our processor group. We have here filtered noise. We also have parameters for the filtered noise. So the filtered noise synthesizes audio by filtering white noise. And we have also the filtered noise subtractive synthesizer here. They explain that natural sounds contain both harmonic and stochastic components. The harmonic plus noise model captures this by combining the output of an additive synthesizer with a stream of filtered noise. And this was shown by Serra and Smith in the 90s and Beauchamp in 2007. So they are able to realize a differentiable filtered noise synthesizer by simply applying the LTV FIR filter from above to a stream of uniform noise. And here they explain the filter design and how they got this harmonic oscillator and the filtered noise. Then we also have here the losses. So they're using this spectral loss. So if we go here, the DSP, we will have losses. We have a base class for all the losses, and here we have the spectral loss. So it is the multi-scale spectrogram loss. It is also here part of our autoencoder architecture, and we have some parameters for the spectral loss. And they say here that this loss is the bread and butter of comparing two audio signals. It offers a range of options to compare spectrograms, many of which are redundant but emphasize different aspects of the signal. And by far, the most common comparisons are magnitudes and log magnitudes. So here is some words about the multi-scale spectral loss. And they say that the primary objective of the autoencoder is to minimize reconstruction loss. However, for audio waveforms, point-wise loss of the raw waveform is not ideal, as two perceptually identical audio samples may have distinct waveforms, and point-wise similar waveforms may sound very different. So instead, they are using a multi-scale spectral loss, similar to the multi-resolution spectral and amplitude distance in Wang et al. From 2019. So all the parameters we need for the model are here at the operative config. There is still also the reverb, and the reverb will be part of the DSP effects. So DSP effects, and we have here reverb that implements a convolutional FIR reverb. It takes neural network outputs directly as the impulse response. So at this point, we've already seen we have our target audio. We computed the loudness and F0, and we'll have this decoder. The output of the decoder goes to the harmonic audio and the filtered noise. Also, the F0 goes to the harmonic audio. They are added, then it's adding some reverb. Then we have this synthesized audio, and we are using a multi-scale spectrogram loss. At this point here, we understood what the model is doing. We know the parameters of the model, they are here on the screen. We know a bit more about this autoencoder architecture. Next, we can modify these conditions. So for example, we can change thresholds for note detection. We can also shift the pitch to certain octaves or adjust the overall loudness. But this is a topic for the next tutorial.